The center of mass is the location of the average mass of the object or system. I'm trying to say it like that on purpose. I'm not being elusive. A single object can have a center of mass, but a collection of objects, like all the students in the room, we could talk about their center of mass as well. So a system has a center of mass, and individual objects have their own center of mass. The center of mass doesn't have to be a place where there is actual mass of the object. I'd argue that the center of mass of this exists someplace where there is no tape. Would you kind of agree? Because I'm pretty sure it's probably in the middle here. But there's no tape there, but that's where the average mass is. We've never worried about this before. Our problems have, in fact, when we first started talking about dealing with the real rules of physics, when we started talking about Newton's laws, the first thing I had you do is ignore the shape of the object completely and just draw a dot representing the object. Remember that? No matter what it was. A box, a car, a bus, a planet, just represented as a dot, as if that's all that matters. But you probably learned at a young age that pushing one place on an object has a different effect than pushing something else on an object. Probably when you were 2 years old, you went to go push something. You pushed it right over, fell on top of it, screaming and bawling your head off. Mommy was freaking out. I had to go over there and deal with your crying butt and set you all right. Then you learn, though, right? Don't push that way. Or maybe you didn't learn. You went ran over there and pushed it again and fell over again. I don't know. Some of you take several tries at failing before you'll actually do it right. But you probably did eventually learn that if you push on it somewhere else, it won't fall over. Correct? You learn these kind of things when you're young, and you usually do it by trial and error. We've been ignoring that the point of application of a force may make a difference in how the object behaves. We've been ignoring that. We won't be able to ignore it much longer. So that's why we're going to start talking about it by talking about the center of mass. Now, there is something I need to relate. In my definition, I made it very clear. The first word was location. The center of mass is a place. It's not the mass. The center of mass is a location. It's a vector. Right now, the center of mass is at the 50 centimeter mark or quite near it. Would you agree? I'm balancing that meter stick up there, and it's pretty obvious that it's pretty balanced, still there. I think we could probably all kind of just point to it and agree that it's somewhere around the middle. Seems to be where the center of mass is. I'm not bringing this up to be flip about it. The meter stick is very linear, right? It's almost one-dimensional in nature, right? Much longer than it has. If you have an object that's a little bit bigger, maybe more odd-shaped, knowing that this is the equation for the center of mass. And I'm just giving you the one-dimensional equation. If you want the three-dimensional equation, replace the x's with an r, or do one for x, one for y, and one for z. Now, some of you may recognize what this equation is because you've seen it before, probably in a different form. And some of you may not, but this is the equation of a weighted average. You guys probably did that in middle school, weighted averages. In a weighted average, some values are given more weight, meaning they mean more in the average than others. Some people do weighted grades at this school. You've heard that before, right? So one of your things that you might turn in might be worth more points or worth more of a percentage of the average. So a weighted average weights things. This is weighted average. Now, I don't know if you can tell what this says. Many of you are still, once you start seeing those squiggly things, you're just lost. But I've said this before, you don't take notes. You just write down what I've written down. Even now, I'm not so sure that you're going to take any real notes. But I want you to be able to state what this is telling us to do. So, what does this symbol mean? No, that's the name of the symbol. But what does the symbol mean? It's an S for a reason. And I've said this before. It means to add up. It's a sum. So all it means is to add. So I'm telling you to add up every piece of mass right? M, mass. dm or delta m, piece of mass, a part of the mass. So I want you to add up every piece of mass, taking into account where it's located. That's what x means. X is a location. So I'm going to say to you that to find the center of mass of an object, the first thing you have to do is break the object up into little pieces and then add up every piece of the mass, taking into account its location. That's what that says to do. The bottom is even simpler. It just says to add up every piece of mass. I mean, that one should be easy. This is just the mass of the object. Now, the reason I'm bringing all this up is this is the part of the thing that we're not going to talk about till next semester. And I do want to also highlight that you might say, well, why don't you just put mass here? Well, there's a good reason why we leave this as a summation. And one of the reasons is because sometimes we don't have the mass of the object. What if what they gave us instead was a function that was the density of the object? Like what if I have a cloud and I tell you that the cloud is more dense at its center than at its edges? And I don't know what the mass is of the cloud, but I know how big the cloud is. Well, I could calculate its mass. I could calculate it based on the density and perhaps the volume. So there's reasons why this is an integral. This might seem silly, but that might be something like Jupiter is a cloud, right? It's a gas giant. It's more dense at its center than at its edge. There are theories on a description of the density and how it varies from the center of Jupiter to the edge. You could conceivably measure its volume by just looking at it, right? You can measure its size by just looking at it. Well, calculating its mass, or doing the reverse, if you know its mass, you might be able to work backwards to figure out what this density equation is. So that's why this kind of thing exists. Now, we are not going to do that because you're just not there yet. So we're going to do a simpler sum. Right? You know this symbol for sum, don't you? So we can, if we want, instead of using calculus to do this, we could do an estimate by taking our object and physically breaking it into a number of parts. Now, I don't necessarily mean physically breaking it, but maybe separating it into pieces and do the sum this way. We could also use this one if we're dealing with a bunch of individual objects where their shape isn't much different, but they're all spaced out, like you guys. You guys are more or less point masses relative to other people in the room. If I wanted to find the center of mass of the people in this room, I could use this. And just say that most of you take up about the same amount of space. Does that make sense to you guys a little bit? So this is what's called the point mass version of center of mass. So you could find like the center of mass between the Earth and the Moon, which we'll do in a minute. Or in this case, the center of mass of the meter stick as an estimate. So the point mass version still is going to be a location. And it's still going to be a fraction, where the top is one part of that fraction and the bottom is a different summation. If you know how a summation works, then you know that there's a bottom part that tells you what your counter is going to be. I'm going to use the letter I as the counter. I'm going to draw this a little bit nicer so it's easier to see. Use the letter I as the counter. And we're going to start from object 1 to the last piece. Right? It's like an integral. It tells you where to start and where to end. And we're going to add up the position of each piece times the mass of each piece. That's a summation notation. And what this would tell me to do is to take piece 1 and multiply by its mass and its location, and then piece 2 and multiply by the mass of piece 2 and the location of piece 2, and do that all the way until I've reached the last piece. Does that make sense? You know what a summation does, right? An integral is just a summation. This bottom one, though, I'm going to do the same kind of thing. I'm going to start at piece 1 and end at piece n, but I'm just adding up the mass. Each piece, add up all the different pieces of mass, and it should give me the total mass. So here's what I want you guys to do. Let's estimate where the center of mass of the meter stick is. Okay? I want to do so by breaking the meter stick into individual pieces. Now, if you don't understand what this is saying, or what it was saying before, is remember, a piece is a physical piece. I'm taking this as a piece. In this example, I'd say that this piece is just mi, some piece in the middle. In calculus, I would describe this piece as dm, a piece. The thing is, and this part's important, in order to tell you where it is, the first thing I have to do, whether this is an integral or a summation, is to have a point of reference. A place that we are going to agree is how we measure x. So I think for this example, that's a pretty good point of reference, right? Pick one edge. All right, so you have to pick a point of reference. The first thing you have to do in finding center of mass is you pick a point of reference. So I'm going to pick the side there, but that also suggests then that my distance from that point of reference to where my piece is what I'm going to represent as x. All right? So here's what we're going to do. We're going to practice this once. Actually, we're going to practice it twice. I want to do the meter stick example because it's an easy example to do. So to make this easy-ish, we're going to take our object and break it up into pieces. Now, we have to do this in a reasonable amount of time. So let's say that we break this up into 10 centimeter pieces. Does that make sense? I measured the mass of the meter stick earlier today. It's 65 grams. So the whole mass of the meter stick is 65 grams. If I break this up into 10 centimeter pieces, what do you think the mass of each piece is? Good. So we know that if we break up a meter stick into 10 centimeter parts, there'll be 10 of them. That's good. Couldn't get that out of third period. So it's nice to know I can get that out of seventh period. All right, so that starts us, right? We're going to have 10 pieces. We're going to start at piece 1 and go to piece 10. We're also going to assume that every piece is uniform. We're breaking them into 10 centimeter pieces. So we're making a lot of assumptions here. So where do you think the effective center of a piece is going to be if they're 10 centimeters long? Where? 5 centimeters. Yeah, I think it'd be not unreasonable to think that the center of the 10 centimeter piece will be the 5 centimeter mark. All right, so if the first piece's center is at 5 centimeters, where is the second piece's center? Oh, there's a little disagreement in that one. What was that? It'd be 15. That's right. If the first one's at 5, the next one's at 15, and so on and so forth, right? Okay, do what this is instructing you to do. Take a minute and find the center of mass of the meter stick. I've given you a method. We're taking the object, we're breaking it up into pieces, and we're going to do a summation. I think you're going to be summing 10 numbers. You got it? All right. Let's talk a little bit about what you had to do because I'm a little frustrated. Might as well. Let's see. It's a summation. So I'm going to start at piece number 1. Piece number 1 was located, xi is going to be 0.05. I'm just going to do the whole thing in centimeters. So we'll just say 5. And what was the mass of piece number 1? 6.5. Excellent. So we're going to go on to the next piece. Where's the next piece located? 15. That's right. What's the mass of the next piece? 6.5. Okay. And so now you know what you have to do? Because you're going to keep going until you get to the last piece. Right? Now, you guys love to find the easy way out. I hope you have realized that you could multiply each one first and then add them all. But if you're really shrewd like I am, you'll realize that you could pull out that 6.5 because it's the same for all of them. This is a case in which the object has a uniform density. Now, if the object's density was not uniform, And then each of these would be different numbers. It wouldn't be 6.5 every time. That's what makes it a weighted average. But in this case, we're breaking up into uniform pieces. So the weighting ends up being where it is. So if you factor out the 6.5, you can just add up all those numbers first and then multiply just once. So it's either multiply 10 times and then add 10 numbers together, or add 10 numbers together and multiply once. Looking for the easy way out, do the easy way out. But hurry up and tell me that it's 50. We know the answer. Right? It's right now balanced in front of you. So we know it has to be 50. Do the math. Show yourself. Show that it's 50. Did you show it? Did you figure it out? Does it come out to be 50? Because originally, I was going to have you break this up into little 1 centimeter pieces. That would be fun for you, for me, well, for you. Because imagine the first one is at the 0.5 centimeter mark, then the 1.5 centimeter mark, all the way up to the 99.5 centimeter mark. It's a lot of adding. Now, just so you guys know, yes, you get 50, right? The calculus version of this is the same largely. What I mean by that is what you're doing in calculus is the same thing as what we're doing here. We're finding a way to write the mass in such a way that we can increment it, but we're just doing it lots of times. I have 4 minutes, which is not exactly enough to do what I'd like, but I'd like you to try. The Earth and Moon are separated by 384 times 10 to the 6th meters. The Earth is 5.98 times 10 to the 24th kilograms, while the Moon is 7.37 times 10 to the 22nd kilograms. Could you figure out the center of mass between these two using what we just did? If we're trying to start this problem, what I would probably do is recognize that the center of mass is going to lie along a line that connects the two. So that turns that from a 3-dimensional problem to a 1-dimensional problem. And now where would you like your point of reference to be? I would say, let's measure it from the center of the Earth. Right, we need a point of reference. Doesn't matter what the point of reference is, but let's make it easy on us. Now start your summation. Your summation only has 2 things in it. It's not a particularly hard sum. First one's going to be the location of the first object. Let's make the Earth the first object. What's its location relative to the reference point? 0, that's right. That makes that one pretty easy, right? And the mass, 5.98 times 10 to the 20. Doesn't matter. We're going to be multiplying by 0. And let's do the next point. Distance away from the reference point is 384 times 10 to the 6th. And the mass at that point, 7.37 times 10 to the 22nd. There's only 2 objects. It's x times m for each object. Then I have to divide by the total mass of the system. 5.98 times 10 to the 24th plus 7.37 times 10 to the 22nd. All right, now you can do your favorite part where you break out the calculator and you push on the buttons and you get all excited. You'll have no idea if the answer's right or not because it's going to be a big number. And you know I'm not going to let you off the hook. I want to know what it is. I want to know if you got the right answer because there's probably 27 answers in the room and there's only 20 of you. Keep going. We almost there? Anybody have it? 4.67 times 10 to the 6th meters. Do you have any idea if that's, who knows, right? Look, the radius of the Earth, 6.37 times 10 to the 6 meters. Does that help you find some relevance? It's right about there. And yes, that's about where it is, about 2/3 of the way to the edge of the Earth. This is the actual place that the Moon orbits. It doesn't orbit around the center of the Earth, it orbits there. In fact, the earth is wobbling around this point. All right. And I don't know why it's taking so long for some of these things to happen. Right, this was an integral. What did it mean? Well, it's a sum. I'm going to add up how much force it takes to move an object a small distance, taking into account the direction of that force. And I'm going to do that from where the object begins moving to where the object ends moving. Right, that's what that meant to do. That's how you calculate all the work required, the energy necessary to move the object. Is how much force it takes to move it, a small amount. I want you to start reading them like this, because it will make this so much better for you if you do. By saying integral, you might as well be saying a word with which you have no understanding of its meaning. The action of taking the integral, the antiderivative and all that, that's just magic. I mean, yes, there's the fundamental theorem of calculus, but it is a sum. They have found some fancy ways to do the addition for you, but it's still just a sum. I'm not sure it'd be obvious where the center of mass is. Even here, I'm not sure where the center of mass is. I think it's probably more towards this side than this side. Wouldn't you agree? But I also think it's probably more towards this portion than this portion. Right? This is two-dimensional here. And I start getting to objects that are 2 or 3-dimensional, the center of mass is going to have more to it. There'll be a center of mass maybe in the x direction and a center of mass in the y direction. If I go 3 dimensions, there's probably a center of mass in the z direction as well. So again, center of mass is a location. I'm going to expect you guys to be able to do at least one-dimensional problems, but I